In this video, we are going to review some of our integration techniques. Okay, so I want to recap the methods that we have for doing integrals that we've learned up until this point. So the first way that we learned for doing integrals was using a limit of Riemann sums. So that's when we had to take a limit of an infinite number of rectangles, and we did that stuff with sigma notation. It was the very first way that we learned to find the area under a curve. And this method was, in all honesty, it's quite tedious. In most examples, it's quite tedious. And it only really works for, low degree polynomials. Those are the only types of examples that we actually used it for. So we learned this first. The second way that we learned how to do integrals was we could do it using areas. Using areas. And that's something that we could do for definite integrals. So that's when I have an integral and there's like numbers at the bottom at the top, those limits of integration for definite integrals. Even this first way, it's also for definite integrals. Okay, so using areas, but this only works for simple shapes. Only works when the graph is either linear, so straight lines, or it's circular. So when I have circular paths, or maybe part of a semicircle. Okay, so using areas. All right. The third way that we learned was with our basic antiderivative formulas. So our basic antiderivative formulas. So we could do integrals using those basic antiderivative formulas. So let's give an example. So as an example, if I wanted to do the integral of like x to the third dx, well, I can use the reverse power rule, which says add 1 to the power to get x to the 4, and then divide by that power. And this is an indefinite integral. There's no numbers at the bottom or the top, which means that wants a general antiderivative, so I got to put a plus c at the end. Okay, so we have our basic antiderivative formulas. Then after that, we learned U substitution. So there were some types of functions, substitution, where our basic antiderivative formulas weren't going to cut it, and we needed a more sophisticated technique, and that was U substitution. And in this section, the method that we've learned about is integration by parts. So integration by parts. Okay. So integration by parts. So this is just recapping the methods that we've seen so far. I want to end by giving us two quick examples where I want to have you pause the video and try them for a few minutes and see if you can practice recognizing which method is going to be most helpful. So as an example, we have two integrals. For this first one, I'm going to give arctan of x getting divided by x squared plus 1 and then dx. And the second example, I'm going to give x squared and then plus arctan of x. So these two examples. So I want to have you pause the video for about 4 minutes to try these. So it's probably not going to be enough time to finish both of them, although you might be able to finish them. So I mostly want to have you practice your speed. So try pausing it for 2 minutes, trying this one, and see if you can get to the point that you know the correct method that's going to help it. And then same thing for the next one. Pause it for 2 minutes and see if you can get to the point where you recognize, oh, what method is going to work for this. So pause it in 4, 3, 2, 1, pause it. All right, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about each of these. So for this first one, I noticed that, I see arctan here. I also see its derivative in the function, because the derivative of arctan is 1 over x squared plus 1. So when you see a function and its derivative in there, that's a tip off to try U substitution and let U be that original function. So if I let U be arctan, remember arctan is another way of saying tangent inverse, then du, its derivative, is 1 over x squared plus 1. And then of course I write the dx next to it. So doing a u sub on this becomes integral, and the arctan up top becomes u. And then everything else, this dx getting divided by x squared plus 1, well, that's just du. That just becomes du. So I'm left with integral of u. I need that antiderivative. Oh, that's just u squared over 2. Got to put my plus c. And then my last step is to plug back in for u. So that'll give me arctan of x getting plugged back in. That whole thing gets squared over 2 and then plus c. And we got it. We got that first one. All right, for the second one, hopefully one of the things that we can notice is, the antiderivative arctan, that one might look complicated. But the antiderivative x squared, that we know how to do. So it's helpful if we split this up into pieces, because when I'm adding or subtracting functions, I can split it up. So I can do that integral of x squared dx, and then plus the integral of arctan dx. And now the first one's not bad at all, because the first one, that's just reverse power rule. It's going to give me x to the third over 3. For the second one, I don't know how to do the antiderivative of arctan maybe yet. I noticed that if we try u sub and let u be arctan, the derivative of that, 1 over x squared plus 1, it doesn't show up in this integral at all. So u sub probably not going to be helpful. So that's a tip off to try integration by parts. So let's try by parts. Let's write u and dv. So what should u be equal to? So let me think about it this way. Where can I put arctan? Should I put it in u or should I put it in dv? Well, if we put it in dv, we have to do the antiderivative of it to get v. But that's exactly what we're trying to do. So we probably don't want to put it in dv. So let's put it in u. So u is going to be arctan. And then dv is going to be the other stuff, which is just dx. And then du, the derivative of arctan is 1 over x squared plus 1. And then write the dx next to it. V, technically there's a 1 next to this dx. This is 1 times dx. So the antiderivative of that is x. So if we use these parts, this becomes uv, which is arctan of x times x, minus the integral of v du. So v times du would be x times 1 over x squared plus 1, and then dx. Okay, so what we're getting is, let me rewrite this with the x in front. X times arctan of x. And then I got minus this integral. Let's combine this into one fraction as x over x squared plus 1 dx. So now I have to work out this integral, but this integral is much easier than the one that I started with. Let me ask you to do a pause one more time for about 2 minutes to try this integral. Pause it in 4, 3, 2, 1, pause it. All right, so hopefully you did that. Hopefully you paused it to try this one. This one also needs a u sub. So if I do a u sub for this, I'm going to let u be equal to the denominator, x squared plus 1, because then its derivative is 2x and then dx. And I see that derivative in the function. I see it in the numerator. I see x in the numerator. It's just off by this constant multiple of 2, but that's okay. We've seen that that is going to be fine for the purposes of a u sub. So in fact, if I just move this 2 over, I get du over 2 equals x times dx. Let's use that to plug in its integral. So the integral becomes, I got minus integral, and then I see now that x times dx is going to be du over 2. So this whole numerator will be du over 2. So, okay, so that over 2, let's just move it in front, 1/2. And then for my function up top, I'm going to get du. This denominator just became u. And then I can write that more simply as like, I can just move the du to this end of this fraction. And then that leaves me with a 1 up top. All right, so now the 1/2 comes in front. Antiderivative 1 over u is ln absolute value of u. Okay, so now putting this whole thing together, what we get is there was that x to the 3 over 3 in the And then plus x times arctan of x. And now I'm getting minus 1 half ln absolute value of u, and u is x squared plus 1. And then this is an indefinite integral, so I got to put a plus c. Okay. And we got it. So one of the things that I want you to think about as you try integral problems going forward is, really think about, which method is going to be most helpful. And that, it just takes practice to get better at recognizing that. So you want to be patient with yourself as you are practicing these.